Welcome to Tectonic Nights channel. This is day 13 of our series on solving Leetcode problems. Today's topic is sliding window technique. In this video, we'll cover two main types of problems that use sliding window technique. First one is static window length. In this case, we are given a fixed window length and we need to check certain conditions over contiguous subarrays or substrings of that fixed length. Next is dynamic window length. Here the window can expand or shrink depending on whether certain conditions are met. First problem is minimum recolors to get k consecutive black blocks. We are given a string of blocks where each block is either w or b and an integer k which represents the window length. For each possible window of length k, we need to count how many w characters must be changed to b characters in order to transform the entire window into a sequence of consecutive b's. First, we need to iterate through all the possible windows in the string. The number of iterations is given by n minus k plus 1, where n is the length of the string and k is the window size. To clarify this, consider an example string with 10 characters and window length as 7. In the first iteration, we take the first 7 characters as the window. In the second iteration, we move the window by one position and take the next 7 characters, and so on until we reach the end of the string. In this case, there will be 10 minus 7 plus 1, that is 4 iterations. In each iteration, we extract the window by slicing the array and then count the number of w characters within that window. We keep track of the minimum number of w characters across all windows. Each iteration involves slicing the array to get the current window, which is O of k, counting the number of w characters in the window, which is also O of k. The overall time complexity for n minus k plus 1 iterations is O of n into k. Now, instead of recalculating the number of w characters in each window from scratch, we can maintain a frequency count of w and b characters and update these counts as we slide the window. We define a frequency counter for the current window, initially calculating the frequency for the first k characters of the string. Then, as we slide the window one character to the right, we remove the frequency of the character that is sliding out of the window. We must also add the frequency of the new character that is entering the window. That is the character at the right end of the new window. When I is at the last valid index, that is I equal to 3 in our case, the next element that would enter the window is at index I plus k, that is 3 plus 7, 10, which is out of bounds. Hence, we need to check that I plus k is less than n before adding the new element to the window. Each update to the window, removing the old character and adding the new one, takes O of 1 time. Hence, the overall time complexity is O of n plus k. Let's solve a couple more problems that follow a similar format. The next problem is about finding the k beauty of a number. We are given an integer num and a window length k. Our task is to return number of valid windows or substrings of length k that satisfies the following condition, which is the integer value of the substring must be a divisor of num. Now let's dive into the coding section. First, we convert the given number into a string. This allows us to slice the string and check if the substrings satisfy the given condition. We extract the first k-digit window from the string and define it as the current number. For each window of k digits, we check if the number formed by that substring is divisible by num and is non-zero. After checking the current substring, we slide the window to the right by removing the leftmost digit and adding the next digit from the string. Instead of converting the entire substring to an integer at each step, we can update the current number by removing the leftmost digit and adding the next digit using mathematical operations. To remove the leftmost digit, we calculate the modulus of current number with 10 power k minus 1, where k is the length of the window, and to add the next digit, we multiply the current number by 10 and then add the next digit from the string. Let's walk through a couple of examples to clarify. Given number 240 and the window length k 2, initial window is 24, which is the current number. To remove the leftmost digit 2, we calculate 24 mod 10, which gives 4. Now we multiply this by 10 to shift the digits and then add the next digit, which is 0. Now the new number is 40. Next example, given number 9090 and the window length k is 3, initial window is 909, which is the current number. To remove the leftmost digit 9, we calculate 909 mod 100, which gives 9. Then we multiply by 10 and add the next digit 0. Now the new number is 90. Finally, we return the total count of the valid substrings. Next problem is find x sum of all k long subarrays. We are given an array nums of n integers and integers k and x. We need to calculate the x sum for each subarray of length k. The x sum is the sum of top x most frequent elements in the subarray. Note that if two elements have the same frequency, the one with a larger value is considered more frequent. Let's dive into the coding section. We begin by calculating the frequency of first k elements in the array nums. For each sliding window or subarray, we sort the dictionary by frequency first and then by the element value in descending order. Next, we extract the top x most frequent elements from the sorted dictionary, calculate their sum, and append it to the result list. To slide the window, we remove the previous element, decrement its frequency, and then add the next element in the sequence and increment its frequency. Finally, we return the result list. Since we are sorting the dictionary at each iteration, the time complexity here is O of n into k log k. Now let's explore a sliding window pattern with a dynamic window length. First problem is count substrings that satisfy K-constraint. We are given a binary string and an integer k, and our task is to count the substrings where the number of zeros in the substring is at most k or the number of ones in the substring is at most k. Let's see how we can solve this. First, we iterate through the string. We update the frequencies of zeros and ones within the window. Here we are just expanding the window using right pointer. At step 4 and step 5, we can see that window is not valid as both the frequencies of 1 and 0 exceed k. Now let's shrink the window. To shrink the window, we use the left pointer. Initially, we set the left pointer to 0. We check if frequency of 1 and frequency of 0 exceed k. When it does, we shrink the window by incrementing the left pointer and reducing the frequency of the value at left pointer. Now we can see in the output that we shrink the window when the right pointer is at 3 and 4. Let's walk through this example string. When the right pointer r is at index 5, we observe that the window has been shrunk once, but it's still not valid. This is because the frequencies of both ones and zeros exceed k. This demonstrates that simply shrinking the window once isn't enough. We need to continue shrinking the window until it becomes valid. Instead of using an if condition, we can use a while loop to repeatedly shrink the window as long as it remains invalid. After implementing this, we see that when r equal to 5, the window is shrunk twice before it becomes valid. Now let's move on to counting all the valid substrings. To do this, consider the following output. We have printed all the possible substrings for each valid window. For every valid window, we can calculate number of substrings using its window length. R minus L plus 1, where R is the right pointer and L is the left pointer, gives the window length. And by summing the lengths of all valid windows, we can compute the final count of valid substrings. Here the time complexity is O of n. Let's solve another problem with a similar sliding window pattern. The problem is maximum length substring with 2 occurrences. We are given a string S and our goal is to return the maximum length of a substring such that it contains at most 2 occurrences of each character. Let's dive into the coding section. We start by initializing our left pointer to 0 and iterate through the string using the right pointer. As we move the right pointer, we increase the frequency of characters in the window and expand the window accordingly. After each expansion, we check if the window is invalid, that is, if any character's frequency exceeds 2. If the window is invalid, we shrink the window by moving the left pointer to the right until the window becomes valid again. We also track the length of the valid window and update the maximum length found so far. Finally, we return the maximum length of the valid window. Time complexity here is O of n. Thanks for watching. Like, subscribe, and drop your thoughts or questions in the comments. See you next time.